Okay, let's get back to things. So what we want to do now, we've constructed the real numbers, but it doesn't really look much like the real numbers right now. Okay, so let me just remind you. What is a Dedicant cut? A Dedicant cut, it means A union B is the rational numbers. Oops. Okay. A and B are disjoint. A and B are non-empty. Okay. And then for all A and B, A is less than B. Okay. So far, if I have these four things together, what I have is a cut. And to be a Dedicant cut, A has to have, A can't have a greatest element. And now we have a Dedicant cut. And B may or may not have a least element. Okay, so this is what a Dedicant cut, the definition of a Dedicant cut. And then the set of real numbers is just a set of all Dedicant cuts. Okay, and we saw how we could use square root 2 to define a cut, and we could also define any rational cut in a kind of natural way. Okay, and now we want to, so we define R as the set of all C, such as C is a Dedicant cut. Okay. And what we've shown so far is that there is a linear order on the real numbers that preserves the order on the rational numbers. But what we don't know is the least upper bound property, which was kind of the whole point of this construction, is to get this property. Because once you have that, you can prove things like, well, with some work, you can prove things like, I guess I would say the monotone convergence theorem, things like that. I'm not sure if that's the right name for it. Anyways, okay, so if you want to do any kind of analysis, you need the least upper bound property. So what is the least upper bound property? This is like a theorem. Least upper bound property for R. Okay. So let's say we have a subset of R that's non-empty, and there exists B in R such that A is less than or equal to B for all A in A. So all that means is that the set A is a non-empty bounded subset of the real numbers, so upper bounded. Then it has an upper bound, then it has a least upper bound. So there exists a least upper bound B star in R for A. Okay. Okay, so let's try and prove this. What do we need to do? Well, we take our subset A. We're going to kind of try and define B star. Then we have to prove B star is a real number. And we have to prove that B star is an upper bound. Then we have to prove B star is the least upper bound. Then we'll be done. Okay, so we have to construct B star. We have to prove that B star is a real number. We have to prove it's an upper bound. And then we have to prove it's a least upper bound. That's it. Okay, so let's try that. Okay, first let's define B star. Well, we need to define a real number, which means we need to define a Dedicant cut. So that means I need to define my sets A and B, or I don't want to call them A and B now. I guess I'll just use, I shouldn't have called my set A, huh? I guess I'll just use U and V. And I'll call it U star and V star. Right, U star is just going to be all the elements A, all the rational numbers, I don't want to use A, all the rational numbers R, such that R is in U for some UV in my set A. Okay. So my set A is a set of Dedicant cuts, and I construct this set U star to be all the rational numbers that are in some first coordinate in my set A. Okay, and V star is just going to be all the rational numbers not in U star. Okay, now for free, what we get is that U star intersect V star is the empty set, and U star union V star is Q, because V star is just all the rational numbers not in U star. Okay, so U star intersect V star is empty. U star union V star equals Q, and our claim is that B star this is a real number. In other words, a Dedicant cut. Okay. Okay, so what do we have to do? First, we can show like U star is non-empty. U star not equal to the empty set. Well, this is our first claim. Okay, I'll put this like 1. Why is U star not equal to the empty set? Well, U star is all the things that are in some UV in A. Well, A is not equal to the empty set. That's by hypothesis. So let UV be some element of A. Then UV is a real number. So by definition, U is not equal to the empty set. So let let R be in U, then by definition, R is in U star. Okay. And U is non-empty because this UV is a Dedicant cut. Okay. 2. V star is not equal to the empty set. Well, here we have to use the fact that A is bounded. Okay. So our bound we called B. So let's write that as U comma V. Be our bound for A. We're going to claim that actually, so let R be in V. We claim R is in V star. Okay, suppose not. For a contradiction, suppose not. Well, that would mean that R would be in U star because U star union V star is the rational numbers, all rational numbers. So then R is in U star. U star is the union, is basically all the elements that are in some UV, some element of A. So there exists, I don't want to use UV now. I guess I'll say XY. There exists an element of A where R is in A, or sorry, R is in X. Okay. But B is supposed to be an upper bound for X1, for A. The definition of less than or equal to for real numbers, or for Dedicant cuts rather, is that this thing is supposed to be contained in this thing. So that means X is a subset of U. In particular, this element R is an element of U. And R was supposed to be an element of V as well. So R is in U intersect V, which has to be non-empty, and that's a contradiction. UV is supposed to be a Dedicant cut. Cuts are like the two elements are disjoint. So this is the contradiction. Since U intersect V is supposed to be non-empty, it's supposed to be empty. Okay. So now U star and V star are non-empty, are both non-empty. We now have to show that everything in U star is less than everything in V star. Okay. So let R be in U star and Q be in V star. Okay, and we want to show that R is less than Q. Okay. Then R is in some U, or some UV and A. Okay. Now our claim is that actually Q is in V. Okay, why is Q in V? Well, it's either in V or U, since UV is a Dedicant cut. If Q was in U, okay, otherwise, Q is in U, which means that Q would be in U star as well, but V star is a complement of U star. So this is a contradiction. So that Q is in V star. Okay, so Q is in V. Now UV is a Dedicant cut, as are all the elements of A. So R is less than Q, since R is in U and Q is in V. And so now we've shown that every element of U star is less than every element of V star. Oh, I mean, that's not the end. Okay, so now what we have is a cut. We need to show that we have a Dedicant cut, which means we need to show that we need to show that U star has no greatest element. Okay. So this would be like the third or fourth point, I forget. You need to show that U star has no greatest element. Then we will have a Dedicant cut. Okay. So let R be in U star. Then R is in U for some U, V, and A, right? That's the definition of U star. Okay. But U, V is a Dedicant cut, so U has no greatest element. So there exists R prime in U with R is less than R prime. And of course, R prime is also in U star. Okay, so U star has no greatest element. So now we have a Dedicant cut. Okay. For B star equals U star. V star is bigger than or equal to UV for all UV and A. Essentially, this is by construction. We've defined U star, so that contains all these. Okay. So briefly, I'll just say by construction, U is a subset of U star for all UV and A, because U star is just a union of all these U's. Okay. And therefore, UV is less than or equal to U star V star for all UV and A. So by construction, V star is an upper bound for A. We want to show it's the least upper bound. Okay. So let's see the any upper bound for A. Then what that means is that U is contained in X for all U, V, and A. And therefore, U star is contained in X for because U star is just a set of all the things in all the different U's put together. So that means that U star, V star, less than or equal to X, Y. Okay, so now we are done. We've shown that we have a real number that is an upper bound, and that is the least upper bound of our non-empty bounded set A. Okay, so that establishes the least upper bound property. Okay, in terms of the real numbers, there's still some stuff missing, meaning there's still some stuff that we need to know about them, right? What we need to know is that, okay, sure, we have this this set. It contains the rational numbers. It extends, like less than extends from the rational numbers to the real numbers, and we have the least upper bound property. But what we need to know is like, you know, what we want is that, here's what we want, is that here we had the rational number line with a bunch of holes. We want to just, like the real numbers, to have all the rationals and all the little holes filled in. Okay, you know, so here's square root 2, this is 3, you know, this is 7/2, and so on. And then we also have like -1, we have 0, everything good like that, right? And then what we don't want is all those things and so on, but then like a bunch of extra stuff. Okay, like how do I know that sure, I added in all this good stuff, but maybe I added in way too much. Okay, so what we really want to make sure, we need to make sure that between, let's say, any two real numbers, there is a rational number between them. Right? Because that means that even though we added in all these extra stuff to the rational numbers, no matter what you add, like there's still like the rational numbers living in between all of them, all the stuff you added. Okay, and it just means I didn't add a huge blob of real numbers, which has nothing to do with the rational numbers. Okay, so such a blob would be like kind of unnecessary, and you know, I shouldn't have done that. Okay, so we need to make sure of that. So you have like, I guess, so theorem, the rationals are dense in R. Okay, and let A and B be two real numbers, and there exists then a rational number R such that, oh yeah, and maybe I can assume A is less than B. A is less than R is less than B. Okay. Okay, so I think I will stop here. And maybe I'll just finish, I'll upload a 10-minute video to finish this proof. So that, but you know, I would encourage you to try to think about it before then if you want. Okay. Yeah. So I guess that is it for me today. Yeah, thank you all for coming. Yep, take care, everyone. Oh, I had someone asked the question, when will this session be uploaded? So it has to just finish processing. I'll try and upload it either this afternoon or definitely by the end of the day. I'll try my best to get it uploaded this afternoon. Yeah, but thank you for reminding me though. Okay. Oh, so sorry. I mean, I'm pretty much done, but someone had a question about the assignment. They asked, can number 2 be done differently? And there are probably several different ways to do this question. I just gave you one idea. So if you think of a different way, that's probably fine. There's just a bunch of different ways to do that question. Well, at least 2 ways to do that question that I can think of, and maybe you can think of more, you know, so don't worry about if it's not the same as what I was talking about. Okay. Okay, so I guess that is it. So, you know, see you guys later. Bye.